Welcome to Antarctica Live. I'm your host, Dion. Today's session is all about modelling the Antarctica ice sheet, and I'm joined with Tanner and Maya. Can you explain a little bit about your roles? Tanner, can we come to you first?
Uh, yeah, absolutely. So I guess my role in the DOMINOS project is that I'm working on an ice thickness, a glacier ice thickness and bed topography inversion that sort of uses some assumptions about the friction at the bed, uh, paired with really only using surface elevation measurements to actually back out like what the bed looks like underneath glaciers, which can apply anywhere, whether it be Antarctica or our Arctic and polar regions, wherever. Yeah.
Okay, where do you do this from?
Oh, where do I do it from?
Mhm.
Oh, the University of Michigan, at the climate Department of Climate and Space Sciences and Engineering with Dr. Jeremy Bassis.
Oh, fantastic. Right, Maya, over to you. Can you explain a little bit about yourself and your role in the project?
Yeah, so I'm also a graduate student at the University of Michigan working under Jeremy Bassis. And I actually recently joined the Domino's team, but my role in this project is to understand how warming atmospheric temperatures are influencing melt on ice shelves. So I take a look at projections of future temperatures and how that would impact melt on top of an ice shelf and influence hydrofracturing, which is when there are large crevasses or cracks in ice shelves that might cause integrity issues that might influence collapse. So that's my role that I play in this project.
Wow, I mean, they both sound so interesting. I'm always intrigued to know, how did you get into that? Where did you start? What was your inspiration to join the project and to kind of take that path? I'll maybe start with you this time, Maya.
Yeah, so I actually did not start with ice until I began graduate school. In undergrad, I began with just climate studies. I was always fascinated with how the atmosphere and the ocean are intertwined and work together. Um, and when I came to the University of Michigan, I originally was just doing overall climate, but I met with Jeremy and learned a lot about his influence and Antarctic studies and how that can impact other communities around the world, especially with like this rapidly changing climate and loss of ice. And I just found it super fascinating. So that's how I got involved in this project, and I've enjoyed it ever since.
It, massively important as well. Tana, how about you? How did you find yourself there?
Yeah, so my path is actually pretty interesting. I did physics in undergrad, just general physics. And in the States, we have these things called REUs, which stand for Research Experiences for Undergraduates. It's usually funded by the NSF, I think. And it's like a summer program. You get like 8 weeks, and universities will just basically fund you to go do research. And it just so happened that I applied and got accepted to the University of Michigan's with CLASP with Jeremy, who's my present PhD advisor. And this was, gosh, like 3 years ago now. I was a junior in undergrad. And it was really my first exposure to, I guess, climate science and that sort of realm. And I just really, really enjoyed it. I sort of applied on it on a whim. It's more of like an applied physics thing, which is a little bit different than what I was doing in undergrad. But I just sort of went in and just sort of dove deep into it and like really, really loved it that summer. And then after that, I was like, yeah, I'm applying and I'm going to be working on this for for my future. And then that's just how it all worked out. So
Oh, that's amazing. Both completely different, but really good journeys into this type of career. Um, I obviously don't know much about modeling the Antarctic. So can you explain what's involved in that and why it's so important? Tana, can we come to you first?
yeah, so I think in its most rudimentary sense, modeling the Antarctic, and me and Maya were actually talking about this a little bit beforehand, really can mean a lot of things, but most elementary is that basically you're just making some assumptions about the region or about the physics or about something, and then you're using that physical framework to then sort of find or study something that you don't know. So, in Maya's case, that's looking at, data and then hoping to model maybe time evolution of what these ice sheets or what Antarctica might look like in the future, or you could go backwards as well and what it might have looked like in the past. For me, I'm taking some assumptions about the friction at the bed and the ice bed interface, and then I'm trying to model, well, what does the bed look like beneath the ice, even though we can't see it? So I think that's really it. Usually it requires two pieces, like a physical constraint and I guess a computer to do some calculations. So
Amazing. Maya, have you got anything to add?
Um, yeah, I think the most interesting thing about modeling, like Tanner said, is that it's just inputting a lot of different physical components. So in my case, it's looking at atmospheric temperature and then how does temperature influence ice? When it's hot, it might cause melting. When it's cold, it might cause freezing. So it's taking in a very simple parameter and then seeing the combination of that and other pieces of the Antarctic system work together. So it's looking at the ocean, it's looking at temperatures of the atmosphere, the ice, and in Tanner's case, it's looking at regional topography, or like what is the makeup of the actual continent and how ice sits on top of that. And so all of these things are difficult to measure, but it's very interesting to model. So the computer is the most important piece of our work, I'd say.
Oh, how brilliant. I have some questions that have been sent in, if I can ask you them.
Yeah.
The first question we've got is from Freya from North Halifax Grammar School. And she asks, what does Antarctica look like now compared to 1950? So either one of you can take that question. Do you have a preference?
I mean, I can take it if you want, Tanner.
Perfect.
sure. Yeah, go.
So the biggest difference is when you look at sea ice. So differently from ice shelves or glaciers, sea ice is something that forms free floating on top of the ocean itself. And if you were to look at around 1990s, 1980s, even, back to 1950s, you'd look at Antarctica and the pole and it looked like a huge circle with Antarctica's little cutout, but the majority of that filled in with a bunch of sea ice. And now if you were to look at Antarctica, there would be almost no sea ice at all. And you just see this little kind of cookie cutter cutout of what the continent looks like. So, I mean, that kind of tells you that not only have we seen atmospheric warming, we've also seen ocean warming, which has caused the development or creation of sea ice to decline rapidly. We've also seen like massive collapses of ice shelves around Antarctica. So the perimeter has changed quite a bit from 1950s. One of the most famous ones is Larsen B, which happened around the Antarctic Peninsula. And in 2002, a ice shelf that's, I don't know, like 3,200 kilometers squared in size collapsed in about 2 months, just rapidly. And so the coastline has changed dramatically over there, definitely, as we've seen the temperature warm over the last 50 or so years.
That's incredible. That must be amazing to be able to see the differences and study that. Yeah.
Yeah, amazing. Also, a little scary.
Yeah, very much so. Right, I have another question. It's come from Lanesha from Pearl River High School in New York. They've asked, if the rate of melting remains similar for the next few decades, what percentage of coastal land will be covered after all the ice sheets melt? In addition, they've got an addition, what would change the rate of melting in Antarctica? So it's kind of a two-part question. Tanner, do you want to take this one?
Yeah. So the interesting part of sort of, well, modeling sea level rise is that it's actually a lot trickier than you would think. and it has to do with the fact that the ocean is not, or well, yes, the Earth is not a perfect sphere. There's also topography. Also, those ice sheets that are melting, like in Antarctica, actually have their own gravitational pull. And that attracts water. And so there's, I don't know the answer to this question off the top of my head as far as decadal scales, but I do know that if you look a little further, because there's a lot of variability. I mean, I know Maya's looked at some of this a little bit. You know, decadal scales, there's a lot of noise, but once you start to go out into like the century scales, you start to see that sea level rise and, you know, coastal erosion, it becomes a really serious thing. And I think I forgot the exact number, but once you start to get around 10 meters of sea level rise, which would be totally like within the next 100 or 200 years, like absolutely on, you know, on the table if we continue at current rates, you start to say some pretty serious like coastal cities kind of just get flooded, like Manhattan, New Orleans, Houston, you know, within 100, 200 years, like it's a total possibility that those could be like underwater, which obviously it's a super big deal. There's also, if you think about island nations, maybe things that we don't immediately think about, but that affect other people disproportionately. Totally, you know, a big deal. So that's why we're looking at these things. And I guess what are some things that could change the rates of melt? That's also another tricky issue, and that when it just has to when we think about like radiative equilibrium, we're kind of baked into like temperature rise globally. So even if we stopped emitting carbon right now, and that would be the first thing that would slow down melt, would be stopping emitting carbon. We're still baked in to a couple decades of global warming and temperatures, just because there's the concept of, I guess, thermal inertia. So I guess if we absolutely had to, when we do need to, it would be to stop emitting carbon. And I don't know if Maya has any other ideas on how we'd slow down stopping melting, but I'd say that'd definitely be the biggest one.
Um, no, I agree completely. I think greenhouse gas emissions is clearly the biggest problem. Continuing to emit at the rate that we are emitting is going to only continue to have atmospheric temperatures rise, which causes a lot of issues for ice, obviously, which likes to be at one specific temperature. So I would say that you answered that pretty well. If we continue on our path, I know that Antarctica as a whole has about 60 meters worth of sea level equivalent on its continent. So if all of the ice melted, there would possibly be a rise of 60 meters around the world, and that is terrifying. Also something that will not happen in the next 100 to 200 or 300 years. So we can do a lot to prevent that type of sea level rise by reducing our emissions for sure.
Amazing. Scary. But yeah, scary to think about. But I think great that that's something that your team is thinking about and studying as well. Right, we have another question from Spring Valley High School. They ask, are there satellite towers in Antarctica?
Satellite towers. I would say there are ground observation stations. So these are like weather stations that are scattered around all of the different bases in Antarctica that take a lot of different measurements, including precipitation. So how much does it rain? How much does it snow in specific areas? As well as like basically a thermometer, which takes the temperature of the ground, so what's it actually like on the ice, to about 2 meters higher, and looks at what the air temperature is. And then we also have 10-meter measurements that look at wind speed, these are all factors that play a role in the climate in in Antarctica and around the continent. In terms of satellite measurements, I'm not sure if there are satellite towers, but I know that we do have satellite observations. And there are things like IceSat, which is one of NASA's missions that take a lot of satellite imagery and satellite observations of topography and ice temperatures, etc. Tanner, do you know any more?
I always get confused on this, but there's a whole thing funded by NASA called Operation Ice Bridge,
Mm.
which I think is a grouping of satellite instruments. I always get Ice Bridge and IceSat confused, but there are a number, or at least were a number of dedicated spacecraft or space satellites that take a number of cool measurements from space, you know, for Antarctica, and whether that's, you know, using a laser altimeter to, you know, look at surface elevation, or you know, thermometers for temperature, stuff like that. There's all types of stuff. And, you know, the engineers take care of that stuff.
Oh, well, thank you. We've only got one more question left, and I think this is a question I love. So we've got a question from Kingsbridge International High School, and they've asked, what advice can you offer students who are new to this field and interested in pursuing a career in data modeling? I will ask both of you if that's okay. So can we start maybe with Tanner? What advice would you give to students that
Yeah.
are wanting to pursue this?
Yeah, absolutely. So I guess I have two main pieces of advice, and I'm a little bit biased because I come from a physics background. But I think when you're getting into any type of field that's applied like this, it always will serve you well to understand the like the theory and the mechanisms behind it. Especially we're working in what is basically applied climate physics. I mean, if we can name it any fancy name we want, but that's basically what it is. And coming in with a good understanding, you don't have to be like genius level, but just a good understanding of sort of how things work physically will serve you incredibly well. And I guess the second part would just be you know, just really believe in yourself, and if it's something that you're interested in, you know, follow it. There's going to be times where like it's difficult. Like if this stuff was easy, everyone would be doing it, and sometimes there are days where we're just like, oh my gosh, like this is hard, but we get through it, right? Because you know it takes a certain type of person to really like this stuff. So to anyone who's out there who's interested in this sort of thing, it's incredibly important, because right now our planet is all we have, and we're we're not doing a very great job of taking care of it. So I encourage anyone who's interested in this sort of thing to really go for it.
Perfect. Maya, how about you?
Yeah, I mean, Tanner's advice is great. It's if you are interested in the subject, definitely pursue it. It is an interesting field. There's always something new to learn, and there's so much we don't know. We just said a lot about Antarctica, but there's so much that within the gaps of what we said that is still being studied and still being discovered every day. I think that one of the things that would make me wary, and did make me wary when I first started studying climate, is that everything is modeled primarily, and that means a lot of computer use, and that could be very daunting to someone who's like, oh, I don't know a coding language, I've never coded before. But that is something that, you know, will take time and effort, but you can learn it for sure. And there are so many good mentors out there. Jeremy has been wonderful for us. And I know that at many other universities around the world, there are people who are so willing to help young and inspired students. So even if you feel like you don't have the skills, you can do this and people will help you along the way. So that would be my best advice.
That's lovely. And thank you very much. We're going to end on that note. It's been absolutely wonderful to speak to you both. Don't forget, you can watch all of this week's live Q&As on demand. Thank you for watching.